Okay, do you see my slide?
Yes, we can see your slide.
Okay, good evening, everyone. You can call me Gift as Kai introduced me. And first of all, I have to apologize for my English language because I'm not fluent in English, but I will do my best. Okay, for today, I will present my research paper in the title of Development of Deep Learning Framework for Anatomical Landmark Detection and Guide Dissection Line during laparoscopic cholecystectomy. Okay, before I present the paper, I will provide you some specific words that making us easy to understand the detail inside the paper. As first, I want you to know what is a laparoscopic cholecystectomy. A laparoscopic cholecystectomy is a minimally invasive surgical procedure for removing a gallbladder. And a gallbladder is a small organ like a pear. Look like this. You will see in a green object of this. Okay, if this gallbladder infection from the stone inside here, a patient will feel stomach ache in the upper right of abdomen. So the procedure of this operation is to making a small incision into the abdomen and insert a camera, a special tool for operation. But these operations always have some incident that called bile duct injury. Bile duct injury is a common complication of this cholecystectomy. It happened when the surgeon have a misidentification between a cystic duct at here and the common bile duct at here. Actually, the surgeon have to remove the gallbladder and divide the cystic duct from the common bile duct. But in some time, the common bile duct was cut due to the misidentification from the surgeon. So what is the importance of bile duct injury? Because bile duct is a tube that carry the bile from the liver and gallbladder to the small bowel. So if the patient suffer from this condition, it will make a consequent complication in the future. So this is the reason why we have to find the safe area for dissection. So the safe area for this operation is the upper line of this imaginary line. This line is called R4U line. We adopt the theory of R4U line to develop the algorithm to generate this line for guiding the surgeon during this section. So to generate this line, we have to predict the bounding box of two anatomical landmarks. The first one is the bounding box of lunar sulcus, and second one is the bounding box of the base of segment 4. This one called base of segment 4 because this is the area of this one. This is sorry. This is the area of the fourth segment of the liver. So this area called the base of segment 4. So now we know the foundation of this thesis. And the objective of this research is to develop a deep learning model for real-time detection of the lunar sulcus and the liver base of segment 4, and then generate the guide dissection line like this. So from the bounding block of Louis sulcus and the bounding block of bed of segment 4, we can use the center of each block to be a fixed point that will be a starting point to generate the guide dissection line from this side to this side. And I will show you in the detail in the paper. Okay, let's see. This is the video that we inference after we develop the model. Okay, we inference on the video file after we finish to develop the model, and also inference in the operating room for real-time detection. As you can see, the model detect the Louis sulcus and the base of segment 4, and then generate the dissection line between the center of the left block and the right block. And in this video, you will see the surgeon dissect upper disc line, because it is a safe area for dissection. Okay, now shall we start to see the detail from the paper? I will crossing the slide and open the paper. Okay, do you see my paper?
Yes, we can see your paper.
Okay. Okay. From this paper, the background of this research is, as I introduced before, that we want to prevent the bile duct injury. So we develop a deep learning framework to detect the Louis sulcus and the liver base of segment 4. And we propose the algorithm for generate the guide dissection line. So for the methodology, the result and the conclusion, I will present in the next page. Okay, the introduction, I thought all of you is already know because I present in the presentation, and I will skip this part. And this images is the same as I present. So let's see this picture. Okay. There are 5 steps to do this research. The first one is the dataset preparation. The second one is the dataset splitting. The third one is the training and validation phase. And the fourth step is the testing phase. And the last step is inference for real-time detection. Okay, let's see the dataset preparation. In this research, we collect 40 video from Songkla University Hospital, and then per one video, we capture 80 images. So we got the total number of images in 3,200 images. We trained the model with the still image, not a video. Before we train the model, 3 surgeons have to annotate the Louis sulcus and the liver base of segment 4 first. We use the open source name label IMG to create the annotation like this. And after we got or annotation of 3,200 images. We split the data set into the training set, the validation set, and the testing set. Is 70%, 10%, and 20% like this. So after that, we use this data set, the training and validation set, to train the model and validate the model. We use YOLO version 7 to train our data set. We have no modify this model. We just download from GitHub, and then we set some hyperparameter, but we didn't use any pre-trained weight. We train our model with our data set, and then we fine-tuning it by annotated data sets, because 3 surgeons have a different annotation. Some annotation was wrong. So after we got the model from the first state, we have to look at why we got only this accuracy and where is the problem. So we found that the problem is in the annotation phase from the surgeon. So after we finish training the model, we test the model, and we integrate the guide dissection line algorithm into our model in inference phase. So when the model predicts the bounding box, the model will generate this line together. After this, the surgeon will evaluate this line located correctly or not. So the evaluation will separate into section. The first is evaluate the model, and the second to evaluate this line. After we got the model, we infer this model for the real cases in the operating room of our hospital, and it's pretty good. Results is fast because the YOLO V7 are quite small. I think it's only 37 million parameter, not too big, and we can use a laptop to inference for the real case. Okay, for the next page. This paragraph is about the literature review. This research have not much researcher to do. It is have only this one. Oh, sorry. I have only this one that propose the real-time object detection on YOLO V3 for identify 4 landmarks. It just detect 4 landmarks. No further, no additional algorithm, no have a guide dissection line, just detect the anatomical landmarks of cystic duct, common bile duct, lower edge of left median segment, and the luvial sulcus. And another research is they propose the go-no-go-net. This is use a heat map to visualization where is the safe and where is the unsafe area to dissection. So from that, at that time, in 2022, there are no research that have a specific the real-time visualization for guide dissection line. So the reason why we do this because it's new. No one do this, and it's practical. We can use this model in the real situation. So, okay, this paragraph is the objective of our research that I already present, that we propose the deep learning framework to detect Louis sulcus and the liver-based op segment 4. And okay, let's see the data collection and the annotation. Okay. From 40 LC video that we collect, as I present in the picture, that we capture 80 images per one video. In the annotation phase, there are 3 types of Louis sulcus. If you see in this picture, the first one is called slit type. It look like this slit type is similar to the open type because we can see the line of this and this. But for the scar types, it look like this. This type is very hard to detect because it's no the clear line, no the hole. It's just like a scar of this. And for the annotation, the surgeon will be separate the Louis sulcus into slit type, open type, and scar type. And for the liver-based op segment 4, it have only one type of this. And 3 surgeons annotate separately. Each surgeon annotate total number of 3,200 images. So that's why it have the overlap, it have the difference. We have to choose after we got the annotation from the surgeon. Okay, this is the detail that we annotate the liver-based op segment 4, the slit type, open type, scar type of the Louis sulcus. And for the total number of 3,200 images, the training set was divided into 2,240, and for the validation set is 320. And we test the model with 640 images. For the distribution of each class of this is contain 1,646 images of liver-based op segment 4 inside total number of this. And the slit type of Louis sulcus, there are 1,166 images. For open type is 1,702. And for the scar types, the number of images only 273 images. So there are an imbalance cases in this research, and we plan to collect more these types until the number of video equal to both of this. Because this is not easy to found in the patient, is a hard case. So that's why we have only these images. Okay, after we got the images, we have to pre-process a little bit. For the pre-process, we just resize the images from the original site to 416 by 416 pixel for compatible with the YOLO V7 model that have a specific requirement. And then for the data augmentation, we use the default data augmentation of YOLO V7 model that's called mosaic method. The mosaic method combines 4 images into one images that I will show you in this picture. If you see, the name of this case is case 11_77. This is the model will be see just one images. If we didn't apply the data augmentation or this approach is called mosaic augmentation. After we apply this data augmentation, one images will be the combination of 4 images like this, 1, 2, 3, 4, and this one is 1, 2, 3, 4. The same for this, and this. So for example, if you set the mosaic size equal to 8, the total number that the model will see is 32 images in one training batch. So it will provide more perspective. Okay. Back to this paragraph for the YOLO model. The YOLO model at that time is the newest version of YOLO, but now it's maybe version 9, I think. Okay, the specific that the YOLO V7 difference from the previous version is the extend efficient layer aggregation network, or called ELAN, that they introduced in this model. Is this construct used to enhance the parameter utilization, the computational block, and the feature aggregation by adding the expand, the suffer, and the merge cardinality process in the backbone state. So if I think I show you in this. Okay, ELAN in the yellow box of this ELAN will be appear in the backbone and also in the head of YOLO V7. If we see this is actually inside is a convolutional block that construct in their style and followed by the max pooling convolution is not specific. You can modify all of this, but for many YOLO versions, they use a spatial pyramid pooling layer with cross-state partial network of this that got the feature map from the P5 state of this, and then they provide two-way of this to this, and predict some bounding box of PT state, and from this is to this, and is going to this, and in between this line they have a split line to this and predict the bounding box of P4 state. So the prediction from the YOLO model will be have a 3 state, the P3, P4, and P5, and then they use a non-max suppression approach to produce the final bounding box. They just choose one that have a max confidence and visualize in the output that they choose only this box. Actually, they provide many boxes, right? But in the final output, we will see only one box like this. That we will see only one box of this and one box of this. Actually, there are no minimum of 3 boxes, but they choose okay. This is the architecture of YOLO V7. The number of layer is 415 and the parameter of this model is around 37 million parameter. And for our research, we have the initial training phase and a fine-tuning phase. We will show you in the table of hyperparameter table. We train the model with initial first, and then we fine-tuning with the re-annotation of the images in the data sets. The first training, we train 100 epochs, and we set the batch size to 16. The image size is 416, and we use a random weight. We know transfer learning the weights from the another model. At this phase, we set the initial learning quite big. It's 0.01 to for faster learning than this phase. And the final learning that we set to 0.1 at the same. For the momentum optimizer and data augmentation, we use a default setting of the YOLO V7. So after we set the hyperparameter, we train the model, we got some prediction, we have re-annotated the images in the dataset. That after that we fine-tuning the model with this hyperparameter. For the next is about the guide decision line algorithm. When we train the model, we didn't produce this guide dissection line. We just add this line into the inference phase because we want to predict some because we just want to use in the prediction phase, not the training phase. And the guide dissection line algorithm receive the input that is the coordinate of Liouville-Shawkat bounding box and the coordinate of the liver base of segment bounding box that collect into the X min, Y min, X max, Y max, and same for both bounding box. And the input of algorithm not only the bounding box, but the corresponding class of each. So the output of this algorithm is a guide dissection line that generates between the center point of these two boxes. to calculate the center of this box is very easy. This one is the bounding box, and we have to find the centroid of this bounding box, right? This will be calculated from this one plus this one and divide by 2. You will got this, you will got the first point of x, that is a center of x. And then for the center of y, you use the value of this one plus with the value of this one and divide by 2. You will got the center of y. So you find the center of this and center of this will be the centroid of your bounding box, like this. This line generate between the center of this box to this box, like this. So this picture can explain this algorithm, and this line I have just shown is incorrect to type of this one. You can use this one. This one is not y mean of Louis Sulcus, but it should be y mean of base of segment 4 plus y max of base of segment 4 and divide by 2. Okay, for the model is Euro V7, the guide dissection line that I show you the proposed algorithm to activate it. And next, for the evaluation of the performance of the model, we use the precision, recall, and average precision for a particular class. It means we use 3 metrics for evaluate base, the lever base of segment 4, the Louis Sulcus of each type. But for the overall performance of the model, we use the mean average precision that got from the average from all of class that provide the average precision. The equation is this one. MAP is for the overall performance and AP is for each class. MAP got from the average of all of AP. Okay, so the result divide into 2 parts. The first part is for the detection part, and the second one is for the guide dissection line. The performance of our model for the validation says that we set the IOU threshold to 0.5. We got the MAP of 98.1% for all class. And for the test set is also we set the IOU threshold to 0.5. We got the MAP is 91.3%. And for the evaluation of guide dissection line, from the test set, we have 640 images for the total, but we have only 360 annotated images that contain both landmark. Some images have only one landmark. For some images have only Louis Sulcus landmark, and some images have only the annotation of the lever base of segment 4. But the images that contain both of landmark have only 360 annotation, have only 360 images. So in this images, the guide dissection line produce 342 images. Do you understand me? Okay, so the surgeon 1, surgeon 2, and surgeon 3 will evaluate from only 342 images, because this one we have a guide decision line visualization, but for another is a wrong prediction. So for this, the surgeon 1 reject 15 images, surgeon 2 reject 6 images, and surgeon 3 reject 23 images. So the average of the rejection is around 4%. After we finish develop the model, we inference in the operating room that we use the laptop with Intel Core i7, 16 gig of RAM, and the NVIDIA GPU of T0X0. So the predict the frame, we predict the frame per second of 30.39. That is fast enough for human eye. So we can see the prediction of the bounding box that quite smooth, not appear and then disappear. So it's okay for this configuration. For the YOLO V7 model, we can use it in the real cases, and it's okay. It's not very good, but it's okay. It's okay. So for the discussion, at this paragraph, I will show you in the table, because it is the detail of the comparison with other YOLO model. We have compared to the scale YOLO V4 and YOLO V5. At that time, these two YOLO is achieved the best, but after YOLO V5, they produce the YOLO V6, but it's not famous, so we choose YOLO V7. Okay, so the MAP of our model is the highest, and the second one belong to the scale YOLO V4. This one produced after YOLO V5 is they produce, as I remember, they produce YOLO V4, YOLO V5, and then scale the YOLO V4. That is better than YOLO V5. And the inference time of our model is just only 0.179 seconds per one images. So the conclusions of our research is we want to prevent the bile duct injury, so we develop a deep learning framework to detect the anatomical landmark that called Louvier sulcus and the liver base of segment 4 to be the fixed point, because we want to generate the guide dissection line to separate between the safe and unsafe area. So if we don't have a fixed point of these two, we cannot generate the guide dissection line, because we don't have a fixed of left point and right point. So this is the idea of Ajahn Siripong from Faculty of Medicine. So I just follow by their idea and its work. We have a presentation at Canada and also this publication for our research. We have next research to detect 4 landmarks and generate 2 lines is for more information that more safer area, and we will start to write the manuscript in this year, we think. Okay, that's all for today. Thank you for your attention. And if you have any questions, feel free to ask me.
Thank you, Pigit, for your knowledge contribution to the women in Myanmar. It's really nice to know how this research works and applying in a real world setting as well. Yeah. So is there any question from the participant? Maybe you can send in the chat or send the message to me so that I can read your question. Okay, I may have one question. In this research, how is there any way to reduce the false positive or false negative errors in this data set?
Yes, we can reduce. Actually, at the first stage, we got really high for positive and for negative. The one that we found, the surgeon forgot to annotate some anatomical landmark, and then the model predict the bounding box. So I compare to the Gauss, why this bounding box have an error. So I saw there are no Gauss. So the model predict correctly, but the annotation is wrong. So this is the one thing that we should be concerned to reduce the false positive, right? And for the false negative, it can be reduced from the re-annotation, because to annotate this, this one, some surgeon annotate like this, very big, very big from this, and this, and then it make the model confused. So in the final state, we have some agreement that we should be annotate like this, only this area is many false positive and false negative coming from the human. From this research.
Okay.
We found a lot of from the annotation.
Yeah.
After the final state is produce the good prediction. So it takes very long time for data engineering process.
That's quite usual for the machine learning projects. Okay,
yes.
we've got another question in the chat box. Hello, in real-time operation, how accurately the model can predict the patient who has never seen by the model? How can the model be certain that the model is not overfitted?
Can I read the chat?
Yeah, you can read in the chat.
Okay. When we predict in the real time or for the real cases, we didn't have any ground truth, right? The evaluation will be coming from the surgeon at the time. But in training and validation process, we have a ground truth, so we can tell how many of accuracy that we got. But in the operating room, we just have the prediction of the confidence along with the box of this one. This one is predict with the confidence of 81, and this one only 0.25. It means the model not sure this is the base of segment 4 or not, but they also predict because these images is coming from some case that we set the threshold below 0.5 for this case. And the overfitting of the model, we can see from the training and validation performance is not, we cannot see the model is overfit in the real situation or not, but we can monitor the overfitting during the training process and the testing phase of this model.
Okay, are there any questions from the participants? P, may I know how you choose the value for the IOU?
For 0.5, right?
Yeah. How you choose based on the experiment?
It's a default. Many research choose this one because it's the middle. But
okay.
If our model very strong, we can choose is 0.8 and still predict the bounding box. Yes, for this one, if we define the IOU to 0.8, it still provide the prediction. But if for this is this box will disappear if we set the IOU to 0.8. It still we have this one.
Thank you. Okay, are there any questions? It looks like we don't have questions anymore. So thank you, Pigit, for your valuable contributions to the Women in AI Myanmar community. So we hope you are participating in the next future